review. Last time, as much as the derivations weren't terrible, last Friday, but especially given that it was basically 2 hours straight, that was probably one of the toughest lectures to sit through. And just remind you where we started out, which was through the Clausius inequality. You derive these types of relationships for total entropy, S and P, use my shorthand. And all right, so don't here now, it's OCD, I gotta fill it out, the word will blow up. Big picture, remember that these energy functions are useful because energy is measurable. They take a stand-in for entropy, which is not. There are no entropy meters. And entropy is the most important thing ever. Changes in total entropy define when something happens versus when it doesn't. But I have no entropy meter, so that really is awful. But with the Clausius inequality, I can stipulate that certain conditions tell me what the changes in energy are of that also dictate whether total entropy increases. There's a minus. Remember that there's a minus t in the derivation, which is why energies actually need to be negative. But also recall that's not hard. You've known that energy goes downhill, and there you're seeing that. The thing we didn't tell you in freshman and high school was that you need to consider these under the conditions under which the process occurs, which is not some kind of funny way of trying to simplify things. Things occur under certain conditions, so if I'm at constant temperature and pressure, I don't need to think about U or H for total entropy. I need to think about constant temperature. That's delta G. Anyway, actually, let me we first introduce A as a new energy function, which is U, which is internal energy, but without the entropy dependence on U, because that sucks. Entropy dependence sucks because I have no good way of controlling it. And so I subtracted out entropy times temperature, which is its conjugate. And that means that A is less than 0 if you're at constant temperature and volume conditions. And delta G, that we are now going to focus the rest of our time on, is relevant under constant temperature and pressure conditions, which since the first week of class, I'd actually been poking you at pointing out to you that these are the conditions that really matter, because the Earth was not built into a giant metal box. We do not need to worry about A for the most part, although we do sometimes do chemical reactions under constant volume conditions, but it's rare, scary. Maybe some geothermal processes. You don't need to look at tables or do Hess's law with G, but A, probably. Not probably, volume is constant, then it is A. We can do things under adiabatic reversible conditions, in which case U and H kick in, whether it's at constant volume or pressure. I imagine that constant volume, again, is just this is all just practical stuff, right? Nothing says that one is more important than the other, but practically that's not true. And G is more important than all the others. So we had to derive all those. I showed you how to do G. You have to do A on your homework, which is just do the same thing as G, just replace H with U. To be perfectly honest, I shouldn't tell you that. And in the next lecture, we also covered a bunch of, God, it was kind of awful. I'm going to actually review some of these, but how do I want to do this? We talked about the change of T, V, and P with constant whatever with changing whatever at constant S. Don't write that down. That's confusing. But just want to remind you again that we were able to look at under adiabatic reversible conditions. We saw that things that we normally take for granted, how like temperature and pressure change, yada, 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 will actually reverse themselves if you're under adiabatic reversible conditions. Again, I did nothing but two-step derivation, but there was like 10 of them or something on that extra hour Friday. The point there is that it shows that you have some ability to do these derivations, especially if they're only 2 or 3 steps, which I value. It also shows you that if I ask you on the test, which I will, that you can logically walk your way through whether the results make sense. And let me pick, I think I did this one. Talk about what you learned in high school. if volume goes up, pressure will go down. And to combat that, because pressure is held constant by my notation, if volume goes up, pressure goes down. And to combat lower pressure, I have to increase the temperature. So that would make this positive. Okay, so again, that's high school level, but now let's do senior college level. Entropy. We'll hold S constant. And let's see, increasing volume drives S down. So I'd have to increase temperature to drive S back up, so that would be still positive, I believe. So this isn't a good example. There was one where it reversed itself. Did he remember? I think that was pressure, temperature. I don't quite remember, but anyway, and I'm actually going to review some of these today, and yeah, so I'm just going to review them. Also, I still want to review, let's forget that. At the end of last lecture, we talked about changes of A. Remember that A itself is not A. None of these functions are useful just in their own right. The changes in the function, like through the cloud system equality, this is what you really want to know. And so we talked about how to solve A and G if we were at constant temperature. At constant temperature, see A is minus SDT, and I do remember these. You would do these, of course, by Legendre transforms, or look at the cheat sheet. At constant T, this is the change in reversible work. And I also showed you that delta G is also the change of reversible work at constant temperature. So again, a gas expands, a gas contracts. You've already gone through how to do U and H. They're both 0 under isothermal. You've got to do the work. Depends whether it's reversible or not. Q is minus that, so yada, 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 yada. S, you use the one formula for that. Don't forget the nuances between total entropy and surrounding entropy. We've gone over that. The last two things are A and G, and just give me the reversible work. Be careful. This is where people, when I ask this, and I definitely will, when I do an irreversible isothermal result, you will forget to calculate the work reversibly. Remember, when I do isothermal irreversible, you're going to calculate the work irreversibly, but when you do A and G, you have to calculate the work reversibly. Don't screw that up. That's the number one way I see people lose 2 points, which doesn't change your grade at all. Okay, now under adiabatic, well, still, you want them, right? Why waste your, if you're going to sit there and calculate it, why do it wrong, right? So under adiabatic conditions, I mentioned to you that when you see a gas expands, a gas contracts, you will not see this asked, and that's because there's no good way to do it. And that's because, let's see, how do I want to do this? Let's do the change in A is the change in U minus the change in TS. And let's do adiabatic. Yeah, adiabatic, this is fine. This is CV dt minus the change in TS. And the change in G would be the same, pretty much the same thing, except a CP instead of a CV minus the change in TS. Okay. Now, adiabatic reversible, I can actually expand this out and keep the change in entropy term constant. Anyway, just forget about it. Big picture, why am I not asking the change in A and the change in G under either adiabatic, that's reversible and irreversible, why do I not ask it? Because this part is child's play, you're halfway there, but at this part you're stuck. Now remember that we often run into equations where we're calculating the change in PV, in which case I insert NR change in T, right? That we saw that a whole bunch of times. All right, so where's my equation for TS right now? Remember, I have an equation for P times V. And when I run into that sucker, I had no problem. But I have no perfect gas equation with a TS in it. TS is equal to da 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 da. I do not have that, and it doesn't exist. Actually, well, it kind of does. There's S, temperature is just temperature, but S is natural log of the number of microstates, which itself is temperature dependent. Anyway, there is no good way to do this. So that's true. So I'm not going to ask that. So anyway, just review. All right, last bit. Now we're on new stuff, so I'll just toss this up here. When it comes to these horrific derivation questions, I am basically done giving you instructions on how to do them. Now everything from here on out is practice. There is one last trick which you do need on the present homework, and you sure as heck need on the next homework, which is called a Maxwell relation. Is that right? Yeah, relation. I couldn't remember whether it was a theorem or a criteria, whatnot. All right, so this is just a little bit of a side trick to getting these derivations to work, because in some of the derivations I ask on the next homework, you're going to run into some derivatives that you really aren't going to have any good way to deal with them, especially like ds dv and ds dt. Okay, that's a good one. And because entropy, the function entropy is again that natural log of number of microstates, what I want to do is replace any derivatives with entropy with them. I want to get rid of them and put something else in its place. Sorry, that's kind of confusing. It's going to make more sense just to show you what a Maxwell relationship is, and a Maxwell relationship is derived this way. I'll derive it, and I'll show you what the relationship is. And I'm going to start with this, TDS minus PdV. Remember, we actually just saw this for the first time. We've been seeing changing U as minus PdV plus heat, and this is heat, is calculated reversibly because I can. And if I choose to do this irreversibly, I can do that. It's just a bloody mess. And why would I? I'm going to get the same answers if I do it this way. As usual, this is the change in F. See, I told you you're going to be sick of this. I hope you believe me. Change in F with respect to X at constant Y, dx plus, right? Remember, this is why PV terms that we keep seeing, this is why this is a biz knocker, because the conjugate of V is negative. So some of you have been tripped up by that, and negatives matter really a heck of a lot. I've been saying that since the beginning. Now you know why. And so, of course, you want to identify, therefore, the change, F is U, obviously, and X is S, and Y is V. This is all hopefully pathetically easy. And what I get from that is du ds at constant V. That's this. This is the conjugate of S, because S is X. This is, of course, T. And change in U with respect to V, change in the constant S is minus P. Right, again, that minus sign is always a real biz knocker. Okay, now what you do, all right, so what, right? Okay, you're sick of it. I hope you're sick of this because that makes it easy. But I want to remind you about the Euler criterion, which when I introduced it, I said I was going to leave it alone and come back to it a month later, as today. Okay, so remember that if F is exact, sorry. If the differential of X is exact, I know that by the following relationship, which is that I can permute the order of differentiation. I'm just writing this down randomly. Don't forget that, unfortunately, this little funky notation, it does matter. So again, I can permute the order of differentiation. Just seems like a math trick, but it's not a math trick when X's and Y's mean something. There you go. And now I can insert, okay, so let's see, df dx at constant Y was U with S at constant V. Okay, so this is this. Okay, so therefore X is S, so this is, wait a minute, am I doing this right? I feel like I had dt. No, I got them switched, didn't I? Sorry. This is bad. Oh, sorry, what am I doing? Sorry about that. I wrote these in the wrong order. Sorry, I really screwed up. I should have done these differently. My bad. Okay, df, dy, right, it's minus p. Okay, sorry. Really screwing up. Okay, I identified x as s. Okay, I've done this part. Y is V, a constant V, but what? Okay, what should I put up here? Right, minus P. Right. So don't forget that in this notation, if you get confused, let's just get mechanical. If you are unfortunately lost, I hope not at this point, but if you are, if this is a letter, it just hops on top, right? Just like that, like somebody writing on the back of a bicycle or something like that. Okay, next side, hopefully I won't blow this. Okay, df dx at constant y, f is u, x is s, y is v, so that belongs here. Sorry again for the big screw up, getting them in the wrong order. So the change in y is again v. It's a constant x, which is s, and what hops on top? Right, there you go. Okay. So the point of this is that when you do these derivations, and you're going to be doing a couple, you may run into something that you just can't handle, and a Maxwell equation is the way out. And I want to remind you that we actually did this last time. It's minus P over CV. So again, let's think of how this could be useful. You've got this sucker here. Yeah, let's say that I have a derivation where you have to do this. And by the way, I know if you run into a biz knocker like this, I know that I'm the one who wrote the question. If you do, I will make it clear what to do because I'm certain you can get the answer, but I don't want you doing it in 20 steps. So if you ran into this sucker here, I would gently remind you of this and this so that you can solve it, right? So PDS, a constant V, would be P over CV. I notice I took care of the minus sign. And wait a minute, did I screw this up? Is this what I was talking about before? Increasing volume, increase. Yeah, didn't I screw this up before? Because this is negative. What did I say before? Because volume goes up, entropy, did I say entropy goes down?
You said positive, but I said positive.
Yeah, but then I did constant entropy. No, I know I said something wrong. I said that this was positive, and it's not. If entropy goes up, volume goes up, entropy goes up, and to drive it back down, temperature has to go down. So, I'm going to do some video. I did say that. No, I didn't say that, did I? No, I didn't. No, I said it was positive. Yeah. I know, but it's negative. So it's negative. I screwed up. But don't worry, I'll send it out of the videos. So, and those of you watching don't know what I'm talking about because I did it. Sorry, yeah, I have to admit, I have to go back. I remember when I was looking at that, I knew I wasn't doing it right, so sorry about that. But again, increasing volume would increase entropy because the gas has more volume. I've already said that that's pretty similar to entropy. To drive it back down, you have to lower temperature, which gives an overall negative. Okay, now hopefully you've clued into the fact that I've gotten a Maxwell relationship. This is a Maxwell relationship. Don't worry about this. This is that jazz we did on the extra hour. This is a Maxwell relationship. And again, I said it gets you out of tough derivations. You notice that I began with the change in U, so do I have other Maxwell relations? Would I have more? Or is that it? Is that the Maxwell relation? What would I do to get more of them? H and A, G. There are 4 Maxwell relationships. Okay, and I will write all of them down without going through that. Now, folks, the main thing here is that Maxwell relationships they're kind of unavoidable in a lot of things. So you're going to see this a lot, as I just said. If I ask you where they come from or ask you to derive it, I would want you to just show me what I just did. But there's a cheat question.
How'd you get a CV?
Now remember that this we solved these in the extra hour on Friday. Okay. Right? No. This is a well, here I can solve it. All right, so that's adiabatic. That's an adiabatic reversible relationship because the change in S is 0. All right, I'm just doing this off the top of my head. Hopefully I won't screw this up like I did a minute ago. That's an adiabatic reversible relationship because I have S constant, and that's only true under adiabatic reversible. Remember that system entropy. And then I remember that I have this relationship. I can relate work to the change in U. And then all I have to do is divide by dV. I got minus P over CV. And by stipulation, but starting out with this equation here, I had to have S constant. Otherwise, I could not have written the first step. So there you go. That's one of the ways. I think I did it in class differently. Again, there's multiple ways to do this. This is the cheap, easy way. So that's where it came from. Just a reminder. So do remember, folks, that extra Friday really was. Is it extra hour? Watch the video again. So that's why I posted those, all right? Okay, so there's three others. Okay, there's one. Let's do the three others. Now, I cannot emphasize this enough. If I ask you to derive a Maxwell equation, which I do every other year, some of you will just write it out. And remember, that means nothing to me. It could be in your calculator. You could have memorized it, which is just pointless. This is not a memorization class. As much as I can help, I know it sometimes degenerates to that. I'd rather not, but we're doing my best, right? So let me write out all the other functions and their Maxwell equations, and let me show you the cheap and easy way to do this. Okay, so this is still TDS and plus VDP. And I always know when I write this one out correctly. Yes, I've memorized it. I always know when I write this one out correctly because it's the one that's all positive. Okay. Now, again, I cannot emphasize enough. Euler criteria, identify a change in F, change in X, change in Y, identify all those species, plug them into the Euler criteria formula, which I don't know where that came from, I'm perfectly honest, or you could do it this way. It turns out that there's this neat little pattern. Dee-da, dee-da, dee-da. Okay. Outer, outer, inner. Just like that. It's really easy to remember. I know you're just like, what? Okay, dt, dp, at constant s. And then permute. dv, ds, at p. You know, I hate trying to teach tricks because it's meaningless, and then you'll probably forget them. Right now, that you will never get wrong. Euler criteria, again, is easy to remember. The change in order of differentiation doesn't matter. That's perfectly memorizable. And if not, it's on the cheat sheet. I look at that formula, I get it right every time. But I swear to God, this is such a time saver. I can't help it. I have to go over this one. But I want you to use this to remember how you got it right. Okay, let's do A. Now, actually, I do want you to recall, sorry, I'll do A in a minute. Let me actually, I think I wrote down from last time. dt, dp at constant s, we did that last time. And that's V over Cp. And the way you can do that, by the way, let me just remind you. So don't write this down because, again, you have it from last time. The change in H is Cp dt under adiabatic conditions, which is dds plus vdp. Okay, adiabatic reversible means this, and therefore, what am I doing? dt dp is v over cp. Right, I'm just doing some algebra. Yeah, okay. Okay, so if pressure goes up, entropy goes down, and so I'd have to drive temperature up to combat that. That's a positive differential. Okay, makes sense. All right, anyway. Okay, more practice with the data. Okay, A I remember is all negative. And of course I'm doing a Legendre transform in my head, but it still retains U's volume dependence, so it's still minus PdV. Okay, all right, let's do it. ds dv at constant t. Okay. Outer, outer, inner, and then inner, inner, outer. Okay, right? So I did that right? I didn't. By the way, I didn't do it right. What did I do wrong? Not minus. Minus signs matter. Minus signs matter. Inner, outer. dp, dt at constant v. I know sometimes it's hard to, maybe hard to distinguish the letters, especially when I'm saying it fast, right? Minus. Yes, minus. Minus. Okay, minus is plus. Okay, so there you go. All right, now this is actually where Maxwell relationships are a bit more useful, by the way. When the derivations you have on the next homework, you're actually going to run into derivations where you need Maxwell equations, the ones that come from A and G. Now, again, the reason is I've got ds dv at constant t. And entropy, remember, is Kb, Boltzmann constant, R divided by Avogadro's number, Ln number of microstates. The number of microstates, as we talked about, is a function of volume. However, I bet it's unbelievably complicated. Yes, by the way, it is unbelievably complicated. That's why you go to grad school. But dp dt at constant v, is that hard? Can you do that?
NR2 over
Not nr.
Oh, LN
No, the t is not over v. There's no natural log. You are integrating not the derivatives, which cost a lot of people a lot of points. P is nRt over v, and you just get rid of the t, right? Just get rid of the t. Okay, so again, homework, exam. You hit this. There's no good answer. You are stuck. You do not leave derivations of derivatives in the form of another derivative. I call that indeterminate. I don't know whether it's up or down yet. That's all I care about. But you show me this, even if you do it this way, okay, with that, I'll accept it. Or look at the Maxwell equations in the back of the book, cheat sheet, and you get nr over v. That's determinate, that's positive. This, I'm not sure. I'm not sure if that's positive, but I know that that is, right? So that's what I need. Last one, change in G. By the way, after this, we're done learning about derivatives. You're still going to be doing them on your homework, but there won't be any more in class, which I actually kind of dislike. And I remember that G is a split, is one that's split. It's temperature and pressure dependent. Okay, so outer, inner, SPT. Okay, then inner, outer. See, it really, it's very easy. Just practice once or twice. And just look back at your notes, dv, dt at constant p. Right?
Minus sign off of it.
Minus sign. People, I keep screwing you on this. That's a point off, right? That's a point off. If you forget these minus signs, you will not get the right answers on the derivations on the homework or the test. These minus signs are actually absolutely crucial just because they are, right? I guarantee you it won't be a matter of, on the types of derivation questions, I don't want to give away too much or make you worry about the future, but on the types of derivation questions I give you, they're designed to return 0, but if you get the minus sign wrong, you won't, right? So that's how you'll know it. Anyway, and of course dv, dt, v is nr, t over t, so that's just nr over t. There you go. Definitely positive. All right, makes sense. If temperature goes up, pressure goes up. Pressure goes up, and to make the pressure go back down, I would increase volume. Right. All right, remember, pressure is held constant, but I increase the temperature, pressure is going to go up. So I have to combat that by increasing the pressure, making that go down, making that positive. All right, makes sense. And again, that's the kind of thing I would have as a early, easy question on homework. Yeah, so anyway, that one, 4 of them. And again, I always make certain that you know which is the one to use on your derivations. I'm not going to leave you hanging like that. I'm not going to leave you with a derivation that requires a Maxwell relation and no way to know that or figure it out. Because if I don't do that, then I'm just setting you up to work in circles, setting you up to get stuck, or getting you to want to put it all on your calculator, which would also be very bad. Explain to your parents why you're being expelled your senior year, right? That's not such a good thing. Last bit, so basically I'm done covering over all the things with derivation. So there's, I'm about to say last bit. No, there is no last bit. That's the problem. So from now on, we're actually going to start taking a fairly radically different approach to all of this, which is all about delta G. So, you know, big picture, you've got all your thermodynamic functions, you've hopefully gained a level of flexibility, seen interconnects to things, you know how to analyze those interconnections. You know, a patient has chest pains but is very overweight and has a stressful job. You've got 3 inputs. Of course, you've got to evaluate the difference between heart attack and anxiety attack. Right? Heart attack means instant surgery. Anxiety attack is just calm down, dude. All right. Those are radically different. Yet anxiety attacks mimic heart attacks almost perfectly. So all of you who want to be doctors, you've got to take those different inputs and see how they're changing and take those derivatives and add and multiply them together to get a right diagnosis. So I think this stuff has some, obviously it's not quite like that, but I think the same skills are there. And also remember that this gas expands, gas contracts. Remember, these are all fiduciaries for actual chemical reactions. So a gas expands would be a chemical reaction that produces more gas, which you are about to do. And all those thermo jazz that you just learned about a gas expands is applicable to a gas reacts to produce more gas, which expands, right? So remember that all this gas expands, gas contracts has all been a stand-in for actual chemical reactions, which just is all the same stuff. It just adds a little bit of a layer of complexity. Now, because of that, because I'm actually going to start doing chemicals now, actual chemicals reacting, I'm going to drop most of those thermo, you're not going to see U again. I'm going to drop them because they're really not relevant. Temperature, constant pressure. I might dip into delta A every now and then just to come up with, you know, a different question that I haven't asked last year or something like that. But for the most part, we're in a delta G world. And of course, I wanted to, you know, that G is Josiah Gibbs. That's who it was named after, who was a turn of the century type of guy, lived in Princeton. I read all about him on Wikipedia, and I swear to God, I almost fell asleep. You know, it's like, what did John Oliver say? I spent all evening reading the Wikipedia page on a rope. I kind of felt like that. So he basically was at Princeton and solved some theorems, and there you go, that's it, dead. Okay, but his dad, Josiah Gibbs Sr., I suppose, actually I think they were both Josiah Gibbs, I think they had different middle names, but anyway, they made a movie about this guy. He was in a movie. I don't think he was Matthew McConaughey. He was in Amistad. Did you guys see that? Wait, seriously, none of you saw Amistad? It was actually recently, yeah, some of you. It was actually recently on Stars or one of those channels that I got like 10,000 of. Okay, you should really watch that. What happened was so Josiah Gibbs' father, Josiah Gibbs, was a lawyer. And it was the only cool thing I can tell you about it, but this is like one of the coolest stories I ever heard. And what happened was there's a ship, the Amistad, that was in Puerto Rico, and they had recently picked up some slaves from Africa. This is the 1840s, by the way. And at this point, the United States had outlawed importation of people. Imagine that. So here's the ship in Puerto Rico full of people. And the Puerto Ricans are looking at them like, what the hell do you think you're doing? You can't do that anymore. And now Puerto Rico isn't the United States, and they're on their way to the U.S. to sell these folks. And they're like, oh no, we just found them in the ocean, right? Now everyone knew what was going on, but there wasn't really a heck of a lot they could do. So here's what happened next. The folks on the ship, they didn't really care for what was happening, so they managed to take over the ship, but they were clever enough to know that the captain and navigator were kind of important to going back home after that long journey across the ocean. So they killed everyone, which I don't blame them for, except the captain and navigator, and said, take us home. Captain and navigator, you know, these folks weren't exactly ship-bearing people. The captain and navigator managed to fool them, and they actually took them to New York. Right? I mean, you know, what the hell? What did they know what was going on? They show up in New York and escape and say, hey, look at all these, you know, these guys took over our ship and killed all these people. Bad people, you know, and the people in New York are like, No, again, like in Puerto Rico, they looked at him and said, no, we know what the heck you're doing, but they have to prove it, right? Court of law, even in the 1840s. The folks on the ship couldn't speak English, and there really wasn't a lot of time to figure it out, right? And so they couldn't tell them that, no, we're from Africa, and if they can't get that out of them, they're screwed. So Matthew McConaughey, he's the lawyer? What? Anyway, he's the lawyer, actually, John Quincy Adams, the son of John Adams, is one of the lawyers as well, or he was the judge. I don't quite remember. But what ends up happening was Josiah Gibbs' father knows that they have to start communicating, and he thinks of this clever way to do it. He goes to the port of New York, which is as diverse as it is now, more so even with more sailors. He stands up on a post and he starts counting from 1 to 10. He learned to count from 1 to 10 in this native language. He's counting from 1 to 10, screaming. Because that's as much, anyone can speak math, right? That's kind of the point of this class. Finally, a U.S. sailor comes up to him, a Navy man, comes up to him and says, he was a freed slave and he joined the Navy. He says, man, what the hell are you talking from 1 to 10 in my native language? He found a translator, right? Wasn't that brilliant? They got that guy to translate from them, which they were able then to prove that they were taken from Africa, and the captain and navigator were thrown in jail, and these people were released. And they lived happily ever after, so don't watch the end of the movie where they tried to go home and they couldn't find it. Africa is actually surprisingly large, right? So it actually ends kind of badly. Anyway, so it's one of the most interesting stories I've ever heard. It didn't have innocence, but it had his father. And hey, math, right? So, okay, blah, blah, blah. Let me continue from here and talk about how we calculate changes of G. Right, before I integrate it, I have to do the small, the differential, and then we'll worry about integrating it and get the big change in G. And what I get from this is that G, let's see, if I'm at constant, what I want to do, at constant t, the change in G will go, so that would, change in G will go up if the change in pressure goes up. Okay, you can see why, and that's because, sorry for my shorthand, dg dt at constant t is v. Right now, hopefully you're all more than okay with df dx, df dy at constant blah, blah, blah to see that. Okay, G goes up if pressure goes up at constant t. Okay, now let's do another one. So this is kind of brainless. And I would actually kind of call that bad. Let's call that bad. Why? Because remember that we're going to live in a constant temperature pressure world, and we want things to happen, right? Things need to happen, and that means delta G is negative. Delta G is negative. That means total entropy increases, again, at constant temperature, constant pressure. And why am I putting my chemicals in a pot unless I want them to react, but unless I want the drug to inhibit the protein, unless I want the chemical to make a semiconductor, right? Why would I put things in a pot if they don't react? Maybe pure discovery, but anyway, for the most part, that's not what us people do, is throw stuff in a bucket and hope that nothing happens, right? So G going up, I call that bad, right? Now that's not such a good thing, good way to put it, because again, G going down is good, that's why I call G going up bad, but remember that if you can say somehow make the G of reactants go up, then the G of the products is down, and that's a negative delta G. So don't forget that. You don't need to remember that, at least not now. Okay, now let's look at temperature. So G will go down if the change in temperature goes up, and that's because dg dt at constant P is minus S, and S is always positive. I don't think. Oh God, I haven't mentioned that. Have I? Yeah, I think I have. I don't quite remember. There are no such things as negative entropies. There are negative changes in entropy, a little unusual, but there are no negative entropies. Remember, KLN, number of microstates, natural logs never return negative numbers. Otherwise, that wouldn't be entropy. Okay, G goes up with pressure, G goes down with temperature. Okay, that's great. But, unfortunately, when it comes to actually getting big delta G, to integrating the partial, right? When it comes to this guy here, this isn't hard. What I do is I say dg is dp and integrate it, right? And that's relatively easy. But the problem here is if I integrate dg is minus s dt, here I'll write that down. So remember, I'm trying to get through this, and so I've got myself this equation. Again, with pressure and volume, that's trivial. I'm not even going to do it because at this point that's blindingly easy. I've got a major problem here. All right, is it this? Is this correct? That's not correct. Why is it not correct?
Interceding in S.
Yeah, remember when I said when can you not bring this out? Right, this isn't constant. This is changing with T. Remember that if temperature rises, entropy changes, system entropy changes. CV ln TF over TI. Don't worry about that. Just recognize that there's a T inside of this. And that means you cannot do this. No. That means that you're kind of stuck. And you are, by the way. So that sucks. All right. All right, it turns out that there's a snarky way out. And here's how you do it. And I'm going to get a new board. This is unfortunately kind of complicated. It is another example of a derivation, stop, another derivation, stop, put together. Understand that's what I'm about to do. And then I'll explain the utility of what I'm about to derive, which is called, I'm going to go ahead and name it, because this is really important. Gibbs-Helmholtz Gibbs-Helmholtz equation. This one is really important. Okay, now again, what I'm trying to do is figure out how to practically get to the change in G as a function of temperature. Because whenever you're doing a chemical reaction and something's not working, you're not going to change the pressure. But you could, but that's kind of crazy, right? How would you do that? Balloon, it wouldn't be too hard, but 2 enzyme in solution, what are you going to do? Put the cell under a high pressure anvil or something? What? No, you're going to change temperature. So practically speaking, I want to see how G changes with temperature. And to do that, I want to remind you that G is H minus Ts. Remember, that's the Legendre transform. And so what I can do is I can try to figure out what S is, right? If I can replace S with something manageable, then maybe this wouldn't be such a biznknocker. And so then what I get is, therefore, minus G over T is S minus H over T. What I did was I multiplied by 1 over, minus 1 over T. Yeah, right? And therefore, S is G minus H over T, and therefore, S is, and therefore dg dt, the constant P, is G minus H over T. Okay. So it looks like I'm kind of getting around this I can't solve this sucker problem because of entropy's complications with temperature. But I've introduced another equivalent problem. I can't solve the change in G on the left with the G on the right. Remember, we've done this several times. Remember van der Waals equation. Remember when I had you do dv dt for van der Waals equation or that other equation? And the problem was you couldn't get V off the right-hand side. Remember, that's why I did that, so that at this moment you would see that you're stuck. And you are stuck, by the way. I gotta get the G over here, and then I'd have natural log of G and some blah, 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 but I can't put it over here. Question?
On the upper board it says dg over dt with constant P is negative S.
What have I done?
Substituted in dg over dt.
Yep. And so, what have I done wrong? I have done something wrong. Wait. Yeah, it's just a minus sign right here, right? Yeah. My bad. Thank you. See that? Yeah, I should have not, I shouldn't have multiplied by minus t, I should have just multiplied by, I should have just multiplied by 1 over t. And then, yeah, I should just, yeah, thank you for pointing that out. Yeah, I'm not doing my algebra very well today, sorry about that. Yeah. Regardless, conclusion is still the same. Okay, real quickly, sorry, I'm almost out of time, so let me show you how you get unstuck. So this is one derivation, which is now at a standstill, so let me do the other and then combine. Okay, so this is an aside, meaning that I'm at a new derivation. What I'm going to do is snarky to get out of it. I'm actually going to take the derivative of g over t. Because temperature is always positive. Temperature is always positive. So if I, and by the reason I'm doing this is because I can solve this, by the way. Temperature is always positive, so that means that in terms of does it go up or down, I can't get it wrong. Okay, now the thing to do is to note that I've got a product rule issue going on here. And so I'm going to leave one function alone, which is 1 over t, and do the derivative of the other, which is dg dt. And again, I'm defining this at constant p. So remember, this is f times g, where f is 1 over t and g is g. Right? So I did that for a reason. Okay, and then the other guy is, I'm going to leave the g function alone, which is g, and then I'm going to do the derivative of 1 over t, which is minus 1 over t squared. Okay, and therefore, I'm going to do this, dg dt at constant p minus g over t. Okay, now, I hate to do this to you, but again, I'm stuck. I'm stuck again. So let's go back to the first. I told you this is kind of awful, all right? Let's look back at this. You see, what I can do with this, I can say dg dt at constant p, it's minus g over t, is minus h over t. Oh, so I just took this leading term and I just subtracted it to the other side. Notice that this and this are the same. And therefore, this is minus h over t, which is minus t squared. Okay. There you go. Okay, and the way that you see this more often, and again, sorry, I'm kind of rushing, I want to kind of screw this up, is in terms of like a chemical reaction where everything is not G but delta G. You just insert the delta, and it's totally fine to do that, and there you go. Okay, the utility of this, by the way, is because the way, remember, entropy is a really hard thing to know what it's doing in any kind of chemical reaction to measure it. You really can't. This thing is actually quite useful. So we're going to do a reaction at constant temperature and pressure. And remember, that means that there's going to be some heat exchange, which means that there is some enthalpy of the reaction. And whether you want to cause delta G to go up or down depends on the enthalpy of the reaction. And let me tell you real quick, and I'll go over it again next time. If something is exothermic, which means delta H is negative, then you actually want to cool the reaction. That would drive delta G down. If something is endothermic, it's sucking in heat. What you do is you raise the temperature, and that will drive G down. So anyway, sorry I'm kind of rushing, but I'm going to go over in more detail this next time, and I'll see you all Wednesday. Remember,